Welcome to this video. We're going to continue the Chapter 7 review of the Stewart 7th edition early transcendental calculus textbook. We were just practicing lots of problems regarding integration and techniques. Okay, so let's begin. We left off on 21. We have this integral of dx over x squared minus 4x. Somehow, the first thing I thought of was let's complete the square because it'll make it into some nicer form, okay? And remember how to complete the square? The term in front of the x has to be 1, which it is in this case, so we take the front in term of the x, the term in front of the x, which is minus 4, we divide it by 2, and we square it, so this would be 4, okay? So to make it a perfect square, we want 4, but to make it equivalent, we have to subtract back 4, okay? If we just add 4, then this integral is clearly not the same as this original integral, right? But if we put plus 4 minus 4, it's the same thing. Totally valid. Okay, so again, it becomes a perfect square when we complete the square, right? So this becomes x minus 2 squared. And then we still have the minus 4. And this looks like a much nicer trig sub that we can do. You can even do a little substitution. U is x minus 2, du would be dx. Then maybe you can see the trig sub a little easier. I just directly went from here, so once again, something squared minus something squared. So I know the first term is the hypotenuse, x minus 2. 4, square root of 4 is 2, that's the other one of the sides, and the square root term is the last side, okay? So as per usual, I want to substitute everything here in terms of theta. So I need dx, so I need to first get x. To get x here, we can use secant, because secant theta is x minus 2 over 2, so 2 secant theta is x minus 2. Differentiate 2 secant theta, tangent theta, d theta is just dx. So we got that. We can sub the whole square root term by, which one? Tangent, because tangent is square root term over 2, so 2 tangent theta is square root term. Okay? We substitute everything in the integral, so dx is 2 secant tangent d theta. Okay? Square root term is 2 tangent. We simplify, so this 2 and this 2 would cancel, tangents would cancel, we're left with secant. This is an integral that we probably should remember. If not, you can just look it up in the table of integrals. This is just ln of secant theta plus tangent theta, and then don't forget plus c. We need to back substitute. What is secant theta? Well, you can use a definition here, or you can use a triangle, since we already wrote it here. Secant theta is x over 2 over 2, x minus 2 over 2, sorry. Tangent theta is square root term over 2 plus c, and this is your answer. The back of the book has it in a little different form. I believe they don't have this divide by 2. So did I get that wrong? Answer no, because we can even, let me just do it here. We can write it as ln half times x minus 2 plus square root x minus 2 squared minus 4 like this, right? Properties of logs, this can be ln half plus ln of that big guy. Okay, don't forget the plus c. ln half is just some constant added to the plus c. So you just get ln, so without the divide by 2 there. That's what the back of the book has. But it's the same answer that you get here, and technically over here should be fine. Okay? Alright, let's move on. Integral t e to square root t dt. Okay? So it looks like integration by parts, except we have a square root t. So maybe let's try to get rid of that. So we let u be square root t. You could differentiate, you could differentiate u from here, but remember the trick where it's a little nicer when we square both sides. So there's no square root. U squared is t. We differentiate from this side. 2u du is dt. So you substitute everything in terms of u. What's t? That's u squared. Okay, that looks like there's a negative there, but there isn't. Okay, it's positive u squared. Let me even write it like that. Okay, and then e to the u with u squared t dt we found as 2u du. So we can simplify a little bit. It'll be 2u cubed e to u du, and this is a classic integration by parts method. We had to do integration by parts 3 times, so that's tedious. So I decided to use the tabular method. Okay, we choose p, well, since it is a u, I wrote it as p and dq. P is the one that we want to differentiate to 0, which would be 2u cubed. Okay, we differentiate until we get to 0. 2u cubed, derivative is 6u squared by the power rule. Derivative of that is 12u, derivative of that is 12, derivative of that is 0. Okay, what's left? E to u, that goes in this column. We integrate as many times. That's simple. The exponent is just the exponent. Go diagonally and alternate sign. Okay, so it's 2u cubed e to the u minus 6u squared e to the u plus 12u e to the u minus 12e to the u plus c. So that's this line here. And then we back substitute u is square root t. So that's what I did here. And that's the answer. Okay? Next, we have this integral dx over x squared plus 1. This I see as something squared plus something squared. Maybe we can do a trig sub, which is what I ended up doing. Can we make a substitution? I don't quite see an obvious one. If we let u be x squared plus 2, du would be 2x dx. There's no x on top, so probably not that. Maybe there is a different substitution, but I don't see it right away. So I just went with trig sub. Okay? Again, set up the triangle, something squared plus something squared. So I know that the square root term is the hypotenuse, and then x is one of the sides and 1 is the other side. So tangent theta is equal to x by the triangle. Differentiate that, secant squared theta, d theta is dx. And then we can sub the square root term, that's just secant theta. Okay? We substitute everything, dx is here, secant squared theta, d theta, x is tangent, square root term is secant. So we can simplify to secant theta over tangent theta, d theta. Okay? How do we solve from here? Well, I just change everything in terms of cosine and sine to maybe simplify. And it looks like we can, because this cosine would cancel, so we're left with 1 over sine theta d theta, which is cosecant theta d theta. This is in the table of integrals. Okay? If you remember, integral is secant. Cosecant is very similar. It's log of cosecant minus cotangent plus c. Okay? We have to back substitute so we have to use a triangle here. What is cosecant? That's 1 over sine. Sine is this over this. So 1 over sine would be this over this. Okay, so that's here. Cotangent is 1 over x, because tangent is x over 1. We invert it, 1 over x. Okay, plus c, and this is your answer. Okay, so that one was not too bad. This one's a classic integration by parts problem. Integral of e to x cosine x dx. You can watch my crash course video, but this is how you do it. Doesn't matter what you let u and dv be in this problem, but I let u be cosine, du is minus sine. dv is e to x, v is e to x. Okay, so uv minus integral v du, that's e to the x cosine x, that's uv, minus integral v du, so it'll be plus integral e to x sine x dx. Do integration by parts one more time. We let u be sine, du is cosine, dv is e to x again, v is e to x. So again, uv minus integral v du, so this is from there, e to x cosine x. So plus e to the x sine x minus integral e to the x cosine x. Okay? We notice that if we call this guy I, okay, this is once again I. So then we solve for I. We move the I here, it becomes 2I. So I is this guy, e to x cosine x with e to x sine x, divide by 2, and then don't forget plus c. Okay. We are almost halfway through 10 problems. Okay, this one was tedious. Was not too bad though. This integral of this rational function 3x cubed minus x squared plus 6x minus 4 over x squared plus 1, x squared plus 2. So we can possibly break it into partial fractions. Why did I know that? Well, first of all, this is a rational function. That's a probably good candidate. Secondly, I see that if we kind of rearrange the terms around a bit, like this 3x squared and the 6x, if we factor out a 3x from both of them, it would be x plus 2, x squared. Yeah, x squared plus 2. If we factor out a 3x from this term and this term, right? So there's a factor of it in there. So maybe that can work. So that's how I thought of partial fraction decomposition, in addition to it's a good candidate because it's a rational function, okay? So since it's a nonlinear term, it's a quadratic term, we have to go ax plus b over x squared plus 1 plus cx plus d over x squared plus 2, okay? So this is equal to this guy, the integrand. So multiply both sides by this denominator. So I didn't write all that out. So that's this line. Ax plus b times x squared plus 2 plus cx plus d times x squared plus 1 is equal to the numerator, because we multiply both sides by the denominator, okay? Here, I think the technique of matching coefficients is easier. Instead of plugging in, you can't really plug in nice numbers. Things won't cancel out. So, except when like x is 0, then actually, would it work if x is 0? You might get something, but in the end, you still have to solve like 3 equations, 3 unknowns maybe, or maybe even 4 equations, 4 unknowns. So I feel like matching coefficients is easier. So how do we do that? We just expand the whole thing out. So I foiled this. That's this line. I'm not going to say the whole thing, but I just expanded everything out. So I expanded this, and I expanded this. So that's this line. Okay? Now we just combine all the x cubed terms together. So that's this guy and this guy. So a plus c times x cubed. Combine all the x squared, that's here and here, b plus d. Combine all the x's, so 2ax and cx, so x times 2a plus c. Okay? And then all the constants, 2b plus d. Okay? Why do we want to do it like that? Well, now we can match coefficients with this side. So what's in front of the x cubed? It's 3. So a plus c has to equal to 3. What's in front of the x squared? A negative 1. So b plus d has to equal to negative 1. 2a plus c has to equal to 6. And finally, 2b plus d has to equal to negative 4. So that's what I wrote over here. And these are easy to solve. Okay, so I picked the a and the c equations here. I subtracted the 2. So we got negative a is negative 3, or a is equal to 3. If a is equal to 3, we can plug into either one. We see that c has to be 0. Okay, similarly, we take this equation and this equation with the b and the d. We subtract them. I get minus b is 3. Negative 1 minus negative 4, so negative 1 plus 4, that's 3. So b is negative 3. When b is negative 3, again, we can plug into either. We see that d has to equal to 2. So now we can write this as, so we plug in our a, b, c, and d into up here. Okay, so we get 3x minus 3 over x squared plus 1. That's ax plus b over x squared plus 1. cx plus d. So we're just left with 2 over x squared plus 2 dx, okay? This is now getting close. We can separate this term, we can break up this fraction into 3x over x squared plus 1 minus 3 over x squared plus 1, okay? Why did I want to do that? Well, this one, you can solve by substitution. I did it in my head. It'll be the log, okay? So 3 over 2 log x squared plus 1. Once again, you can just differentiate to check. If you differentiate the log, it's 1 over x squared plus 1 times 2x, okay? So that 2x and this 2, the 2's would cancel, so we're left with 3x over x squared plus 1, which matches this guy, okay? This guy is arc arctan. This one's also arctan. You gotta be careful of the more general form. If you remember the formula, great. If you don't, you can just factor out the 2, and then you can do another substitution if you don't remember the formula, okay? So you should get 2 over root 2 arctan x over root 2 plus c. And you can simplify this, that's what I did in this line. 1 divided by root 2 is, 2 divided by root 2 is the same thing as 2 times root 2 over 2, if I rationalize the radical. So that's equal to root 2. Okay, that's how we solve this one. A little tedious, but not too bad. Okay, this one, integral x sine x cosine x dx. So here, if you happen to know this identity, sine 2x is 2 sine x cosine x, we can greatly simplify this integral. We have a sine x cosine x here, so it's equal to sine 2x divided by 2. So I did that substitution here, using the identity, okay? And now we can just rewrite this. We can pull the half out, half x sine 2x dx. This is integration by parts. You should recognize this. So once again, I did the tabular method. Our u is what we want to differentiate to 0. So I picked half x. I even took the constant. Okay, so half x, derivative of that is half, derivative of that is 0. Okay, what's left? Sine 2x. That goes over here. We integrate just as many times. So integral of sine 2x is minus half cosine 2x. Integral of that is minus 1/4 sine 2x. Okay, that go diagonal. We alternate signs. So the first term would be negative 1/4 x cosine 2x. Here would be plus 1/8 sine 2x, and then plus c. Okay? this next one, we have the integral from 0 to pi over 2 cosine cubed x. So let me rewrite this. It looks funky. Cosine cubed sine 2x, okay? dx. Let's just rewrite it like that, okay? We can once again use this identity. Sine 2x is 2 sine x cosine x. So then we have one more power of cosine, so cosine to the 4th. And then we have a sine and then a 2. So the 2 I moved outside, okay? So we get this. This is a trig integral that we can solve. We let u be cosine, du would be minus sine. Okay? So our integral becomes 2 integral. We need to change the limits of integration. When x is 0, u is cosine 0, which is 1. When x is pi over 2, u is 0. Okay? So it becomes u to the 4th, negative du. We can flip our limits of integration and add a negative sign out in front. There's already a negative sign here, so 2 negatives make a positive. So 2 integral 0 to 1, u to the 4th du. Okay? So this is just parallel. It'll be 2 times u to the 5th over 5, evaluate from 0 to 1. That's just 2/5. Okay? Alright, this one was also tedious. Integral cube root x plus 1 over cube root x minus 1 dx. So I'm thinking we could maybe substitute something, but what do we substitute? If we substitute u as cube root x, it won't help too much. Maybe because it would be u plus 1, and the du would be the issue, I think, because the derivative of x to 1/3 is 1/3 x to negative 2/3. Then I think it'll get messy. So maybe let's try substituting the denominator, whole denominator. So u is cube root x minus 1. Okay? So remember the trick, instead of differentiating this guy, which will get messy, you can try to get rid of the cube root. So u plus 1 cubed is x. Okay, so I differentiate from here, it's a little cleaner. 3 times u plus 1 squared du is dx. Okay, so we can also substitute the numerator. It's just u, if we add 2 on both sides, then u plus 2 is equal to cube root x plus 1. So I substituted everything, so cube root x plus 1 is u plus 2. Cube root x minus 1 is u, so u plus 2 over u. And then dx is 3u plus 1 squared du. Okay, so that's this line. It looks a little better, and actually, I realized that, okay, let's divide through by this. Actually, before that, it looks like a mess still here, right? But actually, you can just, it's a little brute force. I'm not sure if there's an easier way. I just went through the brute force way. We can expand this whole term out and then distribute both these to all the terms, and then it'll just be power rule everywhere, or maybe log. Okay, that's the worst case scenario. I don't know if that's the worst case, but I don't know what I'm saying. Okay, so that's what I did. It'll be tedious, but I see that it's doable. So I divided through by the u here, so that's 1 plus 2 over u. Okay, the 3 I moved outside in front of the integral, it's constant. U plus 1 squared, I expanded. Okay, and then here I just expanded once again. I foiled this, not foil, I just expanded this. So the first term is easy because 1 times this whole guy is u squared plus 2u plus 1. Okay, and then I distribute the 2 over u to each of them, so it becomes 2u plus 4 plus 2 over u. Okay, that's here. We can combine some terms, like this 2u and this 2u becomes a 4u. 1 and a 4 become a 5, so we can simplify to this. And as I said, it's all power rule except 1 log, so this is doable. So 3 times uq over 3 plus 2u squared plus 5u plus 2 log of u plus c, and then we just back substitute u as this guy. Okay? So this should be the answer. I did not check this one, actually, not that I can recall, so you can double check my work here, but you can see that it was doable. So we just made a substitution where u is the denominator. Okay, we can easily get the numerator by adding 2. And then du, we found by, well, we can get rid of the cube root first and then differentiate to get, dx. So we can find dx like this. And then we just did lots of simplification and then it was doable in the end. Okay. Next, okay, this one, I did it the long way to show how you would do it, but there's a very quick way to do it also. Okay? Remember, I said it in some video, when we have special limits like -3 to 3, when it's symmetric about 0, you should check if it's an even or odd function, right? Remember, if it's odd, then f of -x is -f of x, okay? So what happens if we plug in x as -x here? It'll be minus x over 1 plus absolute value, -x, which is -x over 1 plus x. This is negative of this. So since it's an odd function, we know that the integral is 0. Okay, so that's a very quick way to do this. If you didn't realize that, this would be the long way. Okay, so we know the absolute value changes sign when it's at 0, right? So when we had to break the integral from -3 to 0, it'll be on the -x. And then 0 to 3, it's on the plus x, okay? These are not hard to solve, so I did them one by one over here. We let u be 1 minus x, du is minus dx. We have to change the limits of integration. When x is -3, u is 4. When x is 0, u is 1. X is what? It'll just be 1 minus u, okay? Dx is minus du, that's from here, over 1 minus x, that's just u, okay? We can flip the limits and add a negative sign, and there's already a negative sign here, so it can become positive. So integral from 1 to 4, u minus 1 du over u, divide through by the u, that's 1 over u minus 1. Integrate, that's log u minus u, evaluate from 1 to 4, which is ln 4, minus 4 plus 1, which is ln 4 minus 3, okay? Similar exercise over here, we let u be 1 plus x, du would be dx. Change the limits of integration, I won't go through that. X dx, what's x? That's u minus 1. Dx is just du. 1 plus x is u. Again, divide through by the u, that's 1 minus 1 over u. You integrate, so that's u minus log u, evaluate from 1 to 4. Fundamental thing in calculus, 4 minus log 4 minus 1, which is 3 minus log 4. So we add these two up together, it's equal to 0. Okay, so this is the long way to do it. Short way to do it, obviously much faster. Okay, and the last problem for this video, this one was quite easy. Integral dx over e to x square root 1 minus e to the -2x. So this guy, I see that it's actually e to the -x squared. So maybe we can rewrite it a little bit like that, okay? And then e to the x on the bottom is the same thing as e to the -x on the top. So that's what I wrote here. Why did I want to write it like this? Well, u is e to the -x. If we let u be e to the -x, du would be -e to the -x dx. So the top would be -du. The bottom would just be 1 minus e squared. This you should recognize as arc sine. Minus arc sine of u plus c. And then we back substitute. Negative arc sine e to minus x plus c. Okay? That's it for this video. So as you can see, some of them got a little more challenging. Okay? Which is, so if you're able to get these, then you should be in really good shape. Okay? What did we even go over? Let's review once again. We did some trig sub. We did lots of integration by parts actually. More trig sub. More integration by parts. Partial fraction decomposition with quadratic factors. So that was good. Integration by parts. And then some more challenging substitutions. And then this was an even odd function. And yeah. Okay. So if you were able to do this level problems, I feel like you should be in a good spot. Okay? So please like this video if you found it helpful. And as always, please subscribe to look out for the next set of problems. Or the next video. I don't know what I'll be doing.